The North Atlantic in winter doesn't care about your ship's tonnage. Waves tower 5 stories high, wind screams at 70 knots, and the temperature hovers just above freezing, whilst spray turns to ice on every surface. Between 1940 and 1943, this stretch of grey water became the most contested battlefield of the Second World War, not for land, but for the convoys that kept Britain alive. Here's what seems impossible. British destroyers displacing 870 tons routinely hunted U-boat through storms that forced German destroyers of 2 Kaderschwallers to 400 tons to abandon their missions and run for shelter. The smaller ship won the weather war, and that advantage helped turn the tide of the entire Atlantic campaign. On the night of 17th of February 1943, HMS Vanquisher, a V-class destroyer, maintained station in a force 9 gale northeast of Iceland. Her crew tracked a U-boat contact, whilst their German counterparts aboard Z-class destroyers, built with higher freeboards and supposedly superior seeping, had already turned south toward Norwegian fjords. The Admiralty's patrol reports from that winter tell the same story repeatedly. British escorts stayed on station. German surface raiders withdrew. This wasn't courage overcoming fear. Both navies bred tough sailors. This was engineering defeating engineering, whole design trumping displacement figures, and decades of institutional knowledge about the North Atlantic being forged into steel. The paradox deepens when you examine the specifications. German destroyers looked more formidable on paper. The Type 1934 AE class stood taller out of the water, boasted heavier armament, and carried more fuel for extended range. They were designed by engineers who understood hydrodynamics and stress calculations. Yet month after month, Creek's Marine War diaries recorded the same frustration. Weather conditions forced cessation of patrol operations. Meanwhile, Royal Navy destroyers, many launched before 1940 and considered outdated by peacetime standards, kept hunting. They maintained ASIC contact in seas that should have rendered sonar useless. They pursued surfaced U-boat through conditions that meteorologists classified as survival weather. The Admiralty didn't stumble into this advantage accidentally. British destroyer design carried embedded knowledge from centuries of Atlantic operations, lessons learned the hard way during the Western Approaches campaigns of the First World War, refined through interwar exercises off Scotland's northern coast, and validated every time a gale swept across the Denmark Strait. German naval architecture, brilliant in many respects, had evolved primarily for Baltic and North Sea conditions. The Kriegsmarine expected short, sharp engagements in relatively sheltered waters. They prepared for a different war than the one that actually unfolded. By 1943, this weather superiority became a strategic weapon. U-boat commanders learned to dread winter patrols because British escorts remained operational when German surface support vanished. The Wolfpack tactics that had proven so devastating in 1941 depended partly on German destroyers, providing weather reconnaissance and convoy tracking. When those destroyers retreated to port every time a proper Atlantic storm rolled through, the entire operational chain weakened. British destroyer captains, by contrast, knew their ships would answer the helm in seas that would larger vessels. They pressed attacks in conditions that German doctrine classified as prohibitive for surface operations. What created this asymmetry? How did smaller ships outperform larger ones in the most hostile waters on Earth? The answer lies in a series of deliberate design choices, some dating back to 1918, that sacrificed crew, comfort and peacetime elegance for something far more valuable: the ability to fight when weather became a weapon. The Kriegsmarine's destroyer program emerged from unique constraints that shaped every rivet and frame. After Versailles, Germany couldn't build capital ships until the mid-1930s, so destroyer design accelerated ahead of broader naval strategy. When Admiral Raeder's staff drafted specifications for the Type 1934 class in 1933, they envisioned fleet destroyers supporting battleship operations in the North Sea and Baltic waters where wave periods average 5 to 7 seconds and fetch distances rarely exceed 300 nautical miles. These are choppy seas certainly, but fundamentally different from Atlantic swells that build across 2,000 miles of open ocean with wave periods stretching to 15 seconds. German designers prioritized speed and hitting power. The Type 1934A destroyers could make 38 knots in trials and mounted 5 12.7cm guns, more main battery firepower than comparable British destroyers. To achieve this performance, they rode high in the water with substantial freeboard amidships. The theory held that greater height above the waterline would keep the ship drier in rough weather. Engineering calculations supported this approach for the relatively short, steep waves common to enclosed seas. In the Baltic, this design philosophy worked beautifully. In the Atlantic, it created a floating lever arm that storm winds could torque with terrifying force. The Royal Navy had been designing destroyers for Atlantic operations since the type emerged in the 1890s. Every iteration learned from predecessor failures. The River-class destroyers of 1903 proved too lightly built for North Atlantic patrols. Several broke their backs in heavy weather. The Tribal class of 1907 sat too high and rolled dangerously. By the time the V and W class entered service in 1917-18, British naval architects had accumulated painful wisdom. Destroyers operating west of Ireland needed hulls that worked with ocean swells rather than trying to ride above them. This knowledge crystallized. In the interwar years, when the Admiralty drafted requirements for the A-class destroyers in 1927, specifications explicitly stated these. Ships must maintain combat effectiveness in Force 8 conditions. Winds of 34 to 40 knots with wave heights reaching 25 ft. Not survive, mind you, but fight. That requirement shaped everything. The subsequent B, C, D, E, F, G, H, and I classes that followed through the 1930s refined this Atlantic-capable template. Each class incorporated lessons from winter exercises off Scapa Flow, where destroyer flotillas deliberately operated in foul weather to identify design weaknesses before war rendered such knowledge costly. Geography determined destiny. Britain's survival depended on Atlantic convoys, so British destroyers evolved to hunt submarines in the worst conditions that ocean could produce. Germany's strategic calculus centered on Baltic security and North Sea dominance, at least until Hitler's ambitions outpaced the Kriegsmarine's building program. When war came in 1939, the German Navy discovered it was fighting in waters its ships weren't truly designed for. The institutional culture differed as well. Royal Navy destroyer captains earned their commands through years of North Atlantic experience. They'd served as junior officers on patrol in the western approaches, weathered February gales off the Hebrides, and learned which sea states permitted ASDIC operations and which didn't. This knowledge fed back to the designers at Bath and Barrow. Kriegsmarine destroyer commanders, by contrast, trained in the Baltic, where winter meant ice, not mountainous swells. Their feedback to German shipyards reflected different operational realities. Neither navy was wrong within its original context. Both made rational choices based on expected operating environments. But the North Atlantic doesn't negotiate. It tests every design assumption, and by 1941 those tests were failing one navy whilst validating the other. The bow of HMS Hesperus tells you everything. Stand at dockside in Liverpool and examine where the stem meets the waterline. You'll see the hull doesn't simply cut down vertically into the water. Instead, the forefoot extends deep beneath the surface, whilst the upper bow flares outward in a distinctive curve. This combination, refined across dozens of destroyer classes between 1918 and 1940, represents the Royal Navy's solution to a brutal hydrodynamic problem. How do you prevent a light, fast ship from being thrown sideways or backwards when it slams into a wave taller than the bridge? The flared bow works through deflection rather than confrontation. When an Atlantic roller hits a traditional vertical bow, the water has nowhere to go but up and over, burying the foredeck under tons of green water. That weight up forward pushes the boat down, which can lead to pitch pulling, the ship's somersaulting end over end or at minimum damage to forward equipment and crew injury. British designers angled the upper bow outward at roughly 30 to 45 degrees from vertical. When a wave strikes this flared section, the geometry forces water to split outward and away from the ship rather than climbing aboard. The destroyer still takes spray, certainly, but the bulk of each wave's energy gets redirected sideways where it can't destabilize the vessel. The deep forefoot serves a complementary function. This extended underwater section, sometimes reaching 2 meters below the nominal waterline, acts as a cutting edge that penetrates the wave before the main hull arrives. HMS Jervis and J-class destroyer, launched in 1938, had a forefoot that extended 1.8 meters below her loaded waterline. When Jervis met a 12 MOM's swell, that forefoot sliced into the wave's lower portion, whilst the flared bow above handled the crest. The ship effectively split each wave into manageable components rather than taking the full force as a single impact. This allowed destroyers to maintain 18 to 20 knots through seas that would force a bluff-bowed vessel to reduce to bare steerage weight. Compare this to the German-type 1936A hull form. These destroyers featured more vertical bows with less pronounced flare, a design that worked admirably in Baltic conditions where waves are steeper but shorter. The shallower forefoot, whilst reducing drag in calm water and contributing to impressive trial speeds, provided less bite in long Atlantic swells. When Z-31 encountered heavy weather during operations off Norway in January 1943, her log recorded repeated incidents of the bow lifting clear of the water entirely, the propellers racing as they lost grip, and violent slamming when the hull crashed back down. The ship remained seaworthy, but combat operations became impossible. Gunnery directors couldn't maintain target solutions, and the crew exhausted themselves simply holding on. British destroyers had learned to manage this motion through decades of iteration. The Tribal class of 1938 featured particularly aggressive bow flare, combined with a forefoot that knifed 2 full meters below the waterline. During trials of the Hebrides in February 1939, HMS Cossack maintained 22 knots through force 9 conditions, wind gusting to 47 knots, waves exceeding 10 meters. The captain's report noted, heavy weather working, but ship remains under full control with no reduction in combat capability. That phrase, combat capability, marked the critical distinction. Any properly built destroyer could survive a storm by heaving to and riding it out. British destroyers could hunt through it. The flare also provided crucial reserve buoyancy forward. When the bow did plunge into a particularly large wave, the widening hull shape generated increasing buoyant force that pushed the bow back up before the ship could bury itself. This self-correcting behavior allowed destroyer captains to maintain aggressive courses in following seas, precisely the geometry needed when pursuing a diving U-boat that was trying to use weather as cover. The Hunt-class escort destroyers sat low, almost menacingly close to the waterline, with freeboard midship hips of just 3.22 meters compared to 4.1 meters on German-type 1936 destroyers. They looked like they'd be swamped by the first serious wave. Naval observers from neutral nations who inspected HMS Brecon in 1941 expressed surprise that the Royal Navy considered such a wet deck design suitable for ocean escort work. Then those observers saw Brecon operating in a force 8 gale off Iceland, and the comment stopped. The ship that looked vulnerable proved nearly unshakable. Lower freeboard creates a lower center of gravity. Basic physics, but the implications run deep. Every ton of steel positioned high in a ship raises the center of mass. The further that center sits above the waterline, the more leverage wind and waves have to heel the vessel over. German destroyers with their tall hulls and substantial upper works presented considerable windage in a 40-knot beam wind. Z-29 could heel 12 to 15 degrees simply from wind pressure against her hull and superstructure before a single wave struck. British Vi-class destroyers in identical conditions heeled perhaps 6 to 8 degrees. That difference meant British crews could still service depth charge racks and operate weapons, whilst German crews were clinging to stanchions. The meta-entric height, the measure of initial stability, favoured the lower, beamier British designs. HMS Opportune, a O-class destroyer with 10.7 mm beam and 3 4-meter freeboard, had a meta-entric height of 1.1 ms. This relatively modest figure meant she rolled more gently in moderate seas, which sounds like a disadvantage until you understand the alternative. German destroyers with their higher centers of gravity and taller hulls had lower meta-entric heights, sometimes below 0.9 ms, which produced violent, snappy rolling in storm conditions. This sharp, rolling motion exceeded the ability of fire control systems to compensate. British destroyers rolled more certainly, but they rolled predictably and relatively slowly, allowing gun crews to time their firing and ASDIC operators to maintain contact through the roll cycle. The reduced windage paid dividends in survival scenarios. On 26th of December 1942, HMS Aribe found herself caught in a North Atlantic winter storm with winds exceeding 60 knots. The captain's report described green water sweeping the entire foredeck, but the ship, I know, maintained steerage way and answered helm throughout. The low profile meant wind couldn't get underneath and lever the bow sideways. German destroyer Z-27, caught in similar conditions off Norway 3 weeks earlier, reported her bow being blown 20 degrees off heading despite full rudder correction. The taller hull caught wind like a sail, and in mountainous seas that loss of directional control could drive a ship beam onto the waves, a potentially fatal orientation. British designers accepted trade-offs knowingly. Lower freeboard meant wetter decks in any weather. Crews worked constantly drenched, and seawater invaded spaces that stayed dry on German ships. Equipment suffered from salt corrosion more severely. Living conditions were frankly miserable. V-class destroyers earned the nickname very wetses for good reason, but wet and operational beats dry and harbour-bound. When Admiral Dönitz reviewed U-boat loss statistics in early 1943, he noted with frustration that British escorts maintained effectiveness in weather conditions that his own intelligence staff had classified as prohibiting surface operations. The stability extended to weapons employment. Depth charge rails on British destroyers sat low amid ships where the ship's motion was minimal. On German destroyers, they were positioned further aft and higher where the pitching motion could make safe handling dangerous in rough weather. The convoy designation was JW55B. 39 merchant ships carrying tanks, aircraft, and ammunition to Mormons. They sailed from Loo on 20th December 1943 into weather that even Arctic veterans called exceptional. By Boxing Day, sustained winds reached 50 knots with gusts touching 70. Wave heights exceeded 15 ms, and the air temperature held at 8 degrees C, while spray froze instantly on any exposed surface. This was the Arctic Ocean asserting dominance, and somewhere beneath those grey mountains of water, German submarines were hunting. HMS Obdurate, an O-class destroyer under Lieutenant Commander Charles Slater, held the portwing station. Ice accumulated on her forward gun, mounting at roughly 30 kilos per hour. Ratings armed with wooden mallets worked in rotating shifts, smashing ice off equipment before the weight could destabilize the ship. The ASDIC dome mounted beneath the hull somehow continued functioning despite seas that should have rendered sonar contact impossible. At 0820 hours on 26th of December, the operator reported a contact bearing 287 dig range 1400 YD. In these conditions, it could have been a whale, a temperature gradient, or actual steel. Slater turned to investigate. The German destroyers assigned to shadow JW55B had already withdrawn. Z-29, Z-33 and Z-38 received orders on Christmas Day to intercept the convoy, but by dawn on the 26th all three reported weather damage, forcing return to Alterfield. Z-33's log recorded a fracture in her forward hull plating after repeated pounding, whilst Z-29 lost her forward rangefinder when a wave tore it clean off its mounting. These were not poorly built ships. They'd been constructed to rigorous standards at Germania and Deschimag yards. They simply couldn't operate in conditions that the Atlantic and Arctic Oceans produced with routine malice. Obdurate prosecuted her contact through waves that buried her for deck under 3 meters of water every 90 seconds. The Azdic trace firmed up metallic return, moving at 6 knots. Depth 40 MU1 was attempting to position ahead of the convoy using the storm as cover because no surface ship should be able to maintain sonar contact in force 10 conditions. But British destroyers wrote their own rules about what should be possible. At E847, Obdurate rolled a pattern of 5 depth charges set to 150 and 250 FT. The explosions were barely visible through the spray and snow, but the Azdic operator reported the contact breaking up. Metal-on-metal sounds that meant whole plates separating under pressure. U601 did not survive. Of her crew of 46, none saw home again. Obdurate's log entry remains characteristically understated. Prosecuted contact to destruction. Weather conditions heavy. Resume station 0935 hours. There's no mention of the extraordinary seamanship required to maintain accurate depth charge attacks whilst the ship pitched through 30-degree arcs, or the fact that German surface forces had already admitted defeat against the same weather. HMS Matchless and HMS Musketeer, sister destroyers in the screen, engaged 2 more U-boat that day. Matchless forced U-716 to dive in conditions where the submarine couldn't safely surface again. Her commander eventually had to risk it anyway, and British gunfire finished the job. The engagement reports from all 3 British destroyers note heavy weather, but never suggest it prevented operations. Meanwhile, Kriegsmarine war diaries from the same date record destroyer force abandonment of patrol due to prohibitive sea conditions. The contrast wasn't lost on German naval intelligence. A captured Kriegsmarine analysis document from February 1944 specifically noted British destroyers' inexplicable capability to maintain combat effectiveness in weather exceeding acceptable operational parameters. The analyst couldn't grasp that those parameters had been written for different ships operating in different seas. The engineering failure that doomed German destroyer operations in the Atlantic started in the boiler rooms. Kriegsmarine destroyers mounted high-pressure Ragnar boilers operating at 70 kilos per square centimeters. Cutting-edge technology that delivered impressive power-to-weight ratios in calm water. These superheated systems produced steam at 450 C, enabling the turbines to generate 70,000 shaft horsepower and pushed 2,400-ton hulls to 38 knots during trials. The problem emerged when those same ships encountered sustained heavy weather. Violent motion disrupted water circulation in the boiler tubes, creating hotspots that could cause tube failure. Once tubes started failing, the entire propulsion plant had to be shut down to prevent catastrophic boiler explosions. Z-20 Carl Galster experienced this failure mode on 8th of March 1942 whilst operating northeast of Iceland. 6 hours into a force 9 gale, engineering reported loss of steam pressure in the forward boiler room. Inspection revealed 3 ruptured tubes. The ship had to reduce speed to 8 knots on one boiler, insufficient to maintain heading in heavy seas. Z-20 spent 11 hours wallowing beam to 10-meter waves before conditions moderated enough for her to limp back to Trondheim. British destroyers used lower-pressure Admiral T3 drum boilers operating at 21 kilos per square centimeters. Less efficient on paper, certainly, but far more tolerant of the motion and vibration that Atlantic storms inflicted on machinery. Structural integrity posed equally serious problems. German destroyers employed longitudinal framing for most of their whole length, a weight-saving technique that worked brilliantly for ships operating in sheltered waters. But longitudinal frames concentrate stress along continuous members rather than distributing loads across transverse ribs. When a destroyer's bow slams into a wave, the impact generates torsional stress that twists the entire hull. Transverse framing used throughout British destroyer construction spread these torsional loads across multiple frames. Longitudinal framing channeled them along fewer, more vulnerable structural paths. The consequences appeared in damaged ships returning to German ports throughout 1942 and 1943. Z-25 suffered hull cracking near frame 38 after a North Sea patrol. cracks that propagated along longitudinal stringers. Z-31 developed stress fractures in her keel structure after repeated operations off Norway. Repairs became increasingly complex as dockyard workers discovered cracks had propagated further than initially assessed. By contrast, British destroyers certainly suffered weather damage, but catastrophic structural failures remained rare. The robust transverse framing system, whilst heavier, proved more forgiving of the punishment Atlantic operations delivered. Top weight compounded every problem. German designers mounted 5 12.7 cm guns to match the firepower of light cruisers, an admirable goal that placed significant mass high in the ship. The forward superfiring turret sat 6.5 meters above the waterline, and the twin torpedo tube mounting added another 8 tons amidships at deck level. Fire control directors perched even higher. All this weight above the center of gravity reduced stability margins and increased rolling violence. When Z-29 encountered heavy weather during Operation Front Theater in September 1943, she rolled through 42 degarcs. Motion so violent that unsecured equipment broke loose and several crew members suffered injuries. Ships rolling that severely can't fight effectively even if machinery remains functional. British destroyers carried lighter armament positioned lower, 4 4.7-in guns instead of 5 5-in weapons, and those mountings sat closer to the deck. The sacrifice in broadside weight, roughly 27 kg per salvo compared to 35 kilos for German destroyers, brought precious stability that translated into operational capability when seas turned nasty. The mid-Atlantic gap measured roughly 600 nautical miles across. At its widest point in 1942, that deadly stretch of ocean beyond the range of land-based aircraft where convoys sailed without air cover. U-boat commanders called it the Black Pit and hunted there with near impunity through the first half of 1942. Wolfpack tactics worked because submarines could shadow convoys on the surface, call in reinforcements and coordinate attacks. The only defense was surface escorts, and those escorts had to remain operational regardless of weather. By autumn 1943, British destroyers' all-weather capability had turned the Black Pit into a graveyard for U-boats. The numbers tell the story. In November 1942, convoys crossing the North Atlantic lost an average of 4.2 merchant ships per convoy to U-boat attack. By November 1943, that figure had dropped to 0.6 ships per convoy. What changed? Long-range B-24. Liberators finally closed the air gap in spring 1943, certainly. But equally critical was the Royal Navy's ability to maintain continuous surface escort regardless of weather. German naval analyses from this period repeatedly cite persistent British destroyer presence during heavy weather as a factor degrading Wolfpack effectiveness. U-boat commanders couldn't exploit storms as cover anymore because British escorts continued prosecuting contacts when German surface units had withdrawn. The tactical calculus shifted fundamentally. Prior to 1943, a U-boat caught on the surface in a force 8 gale had reasonable odds of escaping. Pursuing destroyers would struggle to maintain speed and sonar contact. By mid-1943, those odds had collapsed. HMS Hesperus demonstrated this on 11th of May 1943 when she ran down U-223 through a force 9 gales south of Iceland. The submarine attempted to dive, but Hesperus held ASDIC contact through wave heights exceeding 12 water minutes and delivered a depth charge pattern that crushed U-223's pressure hull. Her commander, Captain Lieutenant Peter Gerlach, had previously escaped British destroyers twice by using heavy weather as cover. That tactic no longer worked. Dönitz daily U-boat situation reports from late 1943 reveal mounting frustration. Entry after entry notes contacts broken off due to heavy weather preventing surface operations. But those same reports acknowledge British escorts maintained pressure regardless of conditions. On the 17th of December 1943, Dönitz wrote to Raeder, "The enemy's apparent immunity to weather conditions we find prohibitive has severely degraded Wolfpack coordination. Surface reconnaissance by our destroyers cannot be maintained in Atlantic winter conditions." He was describing a capability gap that technology alone couldn't bridge. This was institutional knowledge embedded in whole forms developed over decades. The operational tempo told its own story. Between January and May 1943, Royal Navy destroyers in the Western Approaches Command logged an average of 24.3 days at sea per month. Kriegsmarine destroyers operating from Norwegian bases averaged 11.7 days at sea during the same period. Weather accounted for much of that discrepancy. British ships sailed and fought through conditions that kept German destroyers in port. Every day a German destroyer spent weatherbound was a day U-boat lacked surface support and convoy tracking. The Wolfpack tactic required coordination. Submarines spreading across patrol lines, one making contact, others converging for mass attack. This required predictable surface conditions and reliable communication. Atlantic storms disrupted both. German destroyers that might have provided weather reconnaissance and radio relay sat in fjords waiting for calmer seas. British destroyers remained on station, forcing U-boat to submerge defensively and lose contact with convoys they'd been shadowing. By the time weather cleared, the convoy had gained 200 miles and changed course. May 1943 became known as Black May in the U-boat service. 41 submarines lost in 31 days. Naval architecture is rarely celebrated in histories of the Second World War. We remember the codebreakers at Bletchley Park, the corvette captains who shepherded convoys through submarine-infested waters, the aircrew who flew exhausting patrols over grey seas. But the engineers who specified hull flare angles and meta-entric heights in the 1920s and 1930s shaped the Atlantic battle as surely as any admiral. Their decisions often made in peacetime design offices without any certainty that war would come determined which navy could fight when the North Atlantic turned savage. The British advantage wasn't technological superiority in the conventional sense. German engineers understood hydrodynamics and metallurgy as well as anyone. Wagner boilers represented advanced thinking, and German fire control systems often outperformed British equivalents in testing. The difference lay in design philosophy rooted in operational experience. The Royal Navy had spent centuries learning that Atlantic weather was as much an enemy as any opposing fleet. That knowledge accumulated through disasters, ships lost in storms, designs that failed in service, bitter lessons purchased with sailors' lives. By 1939, those lessons were encoded in whole forms, stability calculations, and equipment placement that prioritized fighting capability over almost everything else. German naval design evolved under different pressures. Versailles restrictions, Baltic geography, and continental strategic thinking produced ships optimized for a shorter war in enclosed seas. When Hitler's ambitions pushed the Kriegsmarine into Atlantic operations, those ships faced conditions their designers hadn't prioritized. The result wasn't German naval incompetence. C-class destroyers performed admirably in the Baltic and North Sea, where they'd been designed to operate. The North Atlantic simply demanded different compromises, and by the time that became apparent, German yards were committed to designs already in production. The human cost of these engineering choices played out in frozen convoy battles and submarine warfare statistics. Every British destroyer that remained operational through a winter storm was a destroyer that could prevent a merchant ship sinking, could rescue survivors from torpedoed vessels, could force a U-boat to dive before it achieved firing position. German destroyers that turned back in heavy weather weren't failing their duty. Their ships simply couldn't maintain combat effectiveness in conditions that British destroyers handled routinely. The sailors aboard Z-29 or Z-33 were no less brave than those aboard HMS Obdurate or HMS Hesperus. Their ships had been built to answer different questions. By 1944, the Atlantic's verdict was clear. U-boat losses exceeded replacement rates. Convoy losses had dropped to levels that no longer threatened Britain's survival, and the Kriegsmarine had effectively conceded surface control of the North Atlantic. Weather capability contributed significantly to this outcome. British destroyers wrote the standard for what operational in all weather actually meant. Not survival, but sustained combat effectiveness through conditions that would keep most navies in port. Modern naval architects still study these destroyers when designing vessels for high-latitude operation. The flared bow has become standard on ships intended for polar service. The lessons about center of gravity, freeboard, and whole-form resonance remain relevant. Perhaps most importantly, the recognition that ships must be designed for their actual operating environment, not the environment engineers wish they faced, echoes through every maritime design office. The North Atlantic taught that lesson in steel and salt water, and the destroyers that learned it best were the ones that could hunt submarines through storms that forced everyone else to seek shelter.